Assalamualaikum, Bismillahirrahmanirrahim. Hello everyone, this is CHENG324 Postmodern Simulation, Dr. Bassam Hamad, and today we're going to be taking lecture number 23, and our lecture today is going to be about the effects of poles and zeros. Okay, so today we're going to study the effects of poles and zeros. So let's see what are the poles and what are the zeros, and what are the effects of poles and what are the effects of zeros, and what do we mean by poles and zeros, and so on. So going to the poles, I already mentioned something about the poles, and here I'm going to explain the poles in the sense that you just need to calculate the roots of the denominator. And if you calculate the roots of the denominator, you have everything there, and you just can find the value that you want to. Okay, so looking at, I need just to go to the required page. Okay, so looking at what we have here. Okay, we just want to see. Okay, I don't know if this color is nice or not. Let me use a better color. Okay, so that is my transfer function, right? So how do I know that if this is stable or not? I know through the poles. So simply what we are trying to do here, we want to know that if it is oscillatory or it is stable or not, just by looking at the poles. And what are the poles? They are the roots of the denominator. Okay, the roots of the denominator. What about the zeros? The zeros, in which is the first time I mentioned here zeros. So the zeros are the roots of the numerator. Okay, so I have poles and zeros. Okay, so these are the two terminologies that you have here, poles and zeros. And from poles, okay, if I would say that from poles, you're going to know if the system is stable or unstable, and you're also going to know that if it is oscillatory, or it is smooth. So these are very good information that you will know about the poles. What about the zeros? What about the zeros? For zeros, well, for zeros, you're going to know if the system has an inverse response. And what does an inverse response, or sometimes they call it undershoot, okay? Undershoot. Or it will have an overshoot, okay? Or it'll have an overshoot. And can zero affect the stability of the process or not? Okay, so does it affect the stability? There's nothing here about stability, so no, it does not affect the stability at all. It does not affect the stability at all. However, how could we say that the zeros do have an undershoot or an overshoot? It depends on the zeros, but one effect and the other effect could remove the effect of the other, right? So the poles could have an effect on zeros, and the zeros could have an effect on the poles, depending on what? Depending which one is more dominant. Okay, which one is more dominant? And how to know if they are dominant or not? By looking at the S-plane. And the S-plane, as you remember, I told you the S domain is about having the imaginary axis and having the real axis. And the closest one to this y-axis, the closest to the y-axis, is going to be the one in which I'm going to talk about its dominancy, right? So we are going to say that this is dominant depending on what? Depending on how close it is to the y-axis. Okay, and the rule of thumb that this is dominant and this will have no effect if it is like 1 to 10. Okay, if it's like 10 times the effect. Okay, and how are the poles represented? The poles are usually represented as X, and I think so you will understand something else here, but I'll write that again. So the poles are represented as X, and the zeros are represented as a circle. Okay, so that is like a very quick thing that I'm trying to give you as basics, and now we need to understand. Okay, so that was memorizing. Now we need to understand. Okay, so here simply in this problem that I have here, I have no zeros because I don't have an S here. However, about the poles are the ones here you can see, and you can see that this is negative, and these two, they have no real parts and they have only the imaginary part. But these are complex. Complex means what? Means oscillatory, right? So one negative real pole and two pure complex pole. How that would look like? It would look like something like that. Why is it unstable? Due to continuous oscillations. Okay, it's unstable due to continuous oscillations, and actually the reason for that is what? It is because that I have no real parts here, no real parts. Okay, so the simple rule here goes that if all of them have negative real parts, it will be stable, otherwise not. Okay, and here because I have complex roots, and they will dominate the dynamics. So purely complex pole dominate the dynamics. Okay, so what is next? In this example, for example, I have no zeros. Okay, so there's no zeros here. However, looking at the poles, I have 3 poles. Okay, I have 3 poles, and my 3 poles are all negative. So definitely is stable, and it will be like an exponential term. And as you can see here, is beautiful exponential term when it goes to a steady state. It decays as t approaches infinity. Okay, great. So this is one of the things that we have here. It told me that the time constant is about 5.35. How could he know, or how could that person know it's 5.35? So we simply can say that, well, the time to get to steady state value was 35, and 35 divided by 5 is about 7 seconds. So I have an idea that it's 7 seconds. Actually, if you look at it, the steady state exactly arrived here, right here. So it was not 30, it was like 30. If I would say that is like 30 divided by 5, so it's about 6 seconds, depending on the 5 tau rule. Okay, so that is the 5 tau rule. Or you can simply say that I'll take 63.2% of that. So 63.2% is like something somewhere here, and that will be something like again 6.5 or 7. Again, we can see that. Okay, and we're going to come to that, the details of how to find tau. I'm just giving you a hint. So we coming back to the poles again. Here I have no zeros, so I'm concentrating more on the poles. What about the poles? I have one negative real root, would be an exponential term, but I have first complex roots, and since it is complex, that means it's oscillatory, but at the same time it's not a continuous oscillation. It's an oscillation that will go to infinity because I have positive real parts. Okay, and because I have positive real parts, it's unstable. Okay, so my oscillations will be unstable, and in this case you can see how that looks like. Actually, if you give it more time, and you may find that it will be like that, and it goes really down and then it goes really up. Okay, so it is a continuous oscillation. It is something like, if you want to zoom in, it will look like something like that. Okay, and it goes up and down. Great. So what do we have here? Okay, let's see the other example. So we have two types of poles. The poles that are closer to the imaginary axis, they call them dominant poles. And if you have small real parts, means smaller exponential term and slower decay. Okay, so what do we mean by that? That means when you look at here the values, if you look at these values here, and if you try to plot this on an S-plane, so the poles, we have several poles, and one of the poles is minus 4.68, and another pole was here plus 0.3 plus, so it has plus 0.3 and again 0.3 and plus 0.3 and again 0.3, so here. So because these two poles are closer, which cause the oscillatory system, so this is like somehow little negligible. Okay, it will have a little effect. As I said, if it was 10 times, it will have negligible effect. But if it has less than 10 times, it has an effect. And we can see the little effect here, that it delayed where we had an oscillation here, but it couldn't withstand it. The one which will dominate are what? Are these poles here, are these two poles here. Okay, so these two poles here. And if you go up, if you just can recall the example here, so we had here again two poles, we have three poles, sorry, and this one is plus 1 and minus 1, this is minus 1. So it's like all of them are standing with a certain location, so that this is minus 1, and then there's one here standing and another one standing here, and definitely this is standing on the imaginary axis will be very dominant, and that's why it's appearing directly as oscillation. Okay, so the dominant one are the closer one to the imaginary axis. Okay, so we will call dominant, instead of saying slow, we will call them dominant. It's a better terminology in my opinion. Okay, and so then the poles that are farther from the imaginary axis, okay, which means larger real parts means larger exponential term and faster decay. So we will have a faster decay if we have a larger real part, means larger exponential term. Okay, and what does that mean? The poles which are far from the imaginary axis, okay, far from the imaginary axis, they will have large parts and a faster decay. Okay, great. So all what you know about poles, it tells me that if it is stable or unstable. However, it could be stable like that, and we drew that before. It could be stable like that, where there's no complex roots, only like an exponential term. That means only negative real roots. Okay, and if you have negative real part, however you have a complex root of a negative real part, this will look like something like that. It will go like that, and it will be stable. But when you're talking about poles with positive real parts, okay, positive real parts, it could be like that, or if it is with a complex term, so it will go to infinity. Okay, so these are the two things that we have. Of course, you will have pure sinusoidal if you have pure complex poles. That means no real part, and no real part, that means you have no exponential term. And because you don't have any exponential term, there's nothing that takes it up or down, right? Nothing takes up and down. Here there's an exponential taking it up. Here there's an exponential term taking it down. Here there's no exponential term taking it up or down. Okay, and if you have something at the origin, Okay, we call that as an integrating behavior. Okay, so integrating behavior where we have the transfer function is going to be 1 over s squared. Okay, so as we said, the dominant poles are the ones that are closer to the imaginary axis, like these ones here. And then we have some other poles which are far away, right? So, and these two poles, they are unstable because they have positive real parts. So this is the real imaginary axis, this is the origin. So going to the right is positive. So because they are positive real parts, is unstable. Okay, so that's nice. Again, so we are going to talk about zeros now. And here we are going to start comparing. Also, we have zeros which are dominant and other zeros which are not dominant. Forget about the stable and unstable. I'm going to go to the reasons why do we have zeros. I usually always have transfer function. Usually always have a transfer function of y over x is equal to k over tau s plus 1. So we don't have usually an s in the numerator. But how do we have this? We have it if we have two parallel systems, okay? So this can result from two processes in parallel. And how does that happen? So if you have two systems in parallel, if you can recall that if you have them in parallel, you add them. You add these two systems. And when you add those two systems, tau 2s plus 1, this is what you're going to have. You're going to have k1 into tau 1 into tau 2s plus 1 plus k2 into tau 1s plus 1 over tau 1s plus 1 into tau 2s plus 1. Okay, so this is what we have as a system. And we're going to continue with that, taking common factor for the numerator, where we have k1 into tau 2 plus k2 into tau 1 s plus k1 plus k2, right? Plus k1 plus k2 over tau 1 s plus 1 and tau 2 s plus 1. Okay, so that is the equation that we have, and if I want to put this plus 1, I'm going to just divide k1 plus k2. Okay, so put this in the standard form, which is like tau a s plus 1. This will be k1 tau 1 plus k2, k1 tau 2 plus k2 tau 1 divided by k1 plus k2 s plus 1, okay, over tau 1s plus 1 into tau 2s plus 1. So what do we have here? We are going to call this whole thing tau a. So that this will be something like that. It will look like tau a s plus 1 over tau 1 s plus 1 into tau 2 s plus 1. And in this case, we are going to talk about some cases in which if tau a is greater than 0, what will be happening? Okay, and if tau a is less than 0, what we are suggesting? Okay, in this case, if tau a is greater than 0, we are going to have an overshoot. If tau a is greater than 0, it means that I'm having something like 5s plus 1. This is like I took a number just for tau a. Okay, is greater than 0, so s is greater than minus 1 over 5. Okay, or instead of saying greater, sorry, so you're just saying that tau is greater than 0, right? So 5s plus 1 is equal to 0, so s is equal to minus 0.2. In this case, where it is standing on the left hand side. Okay, it is standing on the left hand side of the imaginary axis, and we represent this as a circle, so that is like here minus 0.2. Minus 0.2. So in this case, are we going to have an undershoot or an overshoot? As I said, that if we have it on this side, you're going to have an overshoot. Okay, you're going to have an overshoot. And what does overshoot mean? It looks like the overshoot of the second order process, but it means here in a different terminology, but it means that it's shooting over the set point. Okay, and if tau A is less than 0, which means an example like if I have, instead of saying plus 5, I have, for example, minus 5s plus 1 is equal to 0. So s is equal to 0.2. And in this case, 0.2, I'm talking about like something which is sitting here, right? On the right hand side. On the right hand side. And in this case, if I have something on the right hand side, I'm going to call that I have an undershoot. Or they also have another name for it as an inverse response. Inverse response. Okay, so these are the cases. These are the cases. And actually, if you would like to look more into depth into it, we already got the value of tau A. We have how tau A looks like. Okay, so if we try to work on this tau A, where I'm saying tau A is greater than 0, so I have like K1 into tau 2 plus K2 over tau 1 into tau 1 over K1 plus K2 is greater or under 0, right? So it's over 0 on the right hand side. And in this case, of course, the denominator is going to cancel out, so we will have K1 tau 2 is greater than K2 tau 1. And then you're going to have a condition in which K1 over K2 is greater than tau 1 over tau 2. Okay, and in this condition, what we are trying to say here, is this correct? I think I missed something here. So K1 over K2 is greater than tau 1 over tau 2. It looks fine for me, even though that I have it in my head in a different way. I missed a negative sign. That's why I was trying to remember here. Okay, so that was the negative sign that we forgot here. So what's simply saying that it happens sometime that it has a greater effect, but it is slower. Okay, it's like two tanks. The one of the tank, it has a greater effect as a sensitivity, but it is slower, and the second one has a less effect, but it is faster. Okay, did you get that? Okay, and because of that, of these conditions that we have, we will either have an undershoot or an overshoot. That something is faster or it is more sensitive, it will have an effect little in a different way. And when will this happen? You don't need to concentrate on the condition more than to concentrate if it is going to be dominant or not. Okay, dominant or not. Okay, so we are telling that this condition that we have is going to be effective or not. And how to know this? Let's take some examples. Okay, and in this case, I'm having this is my system. Okay, let me go to here. Okay, so I'm having this system here, and in this system, what do I have? I have zeros and poles, and in the case of zeros, this is 1 over 10 s plus 1 is equal to 0. So s is equal to minus 1 multiplied by 10, so it's minus 10. And of course, you're going to find the poles here, right? And if you find now, this is minus 10, right? So if you draw your S-plane, the imaginary and the real roots, so here we have poles is minus 8. So just say that this is minus 8, and then here's minus 0.6, and then minus 0.18. That's really close. And the zeros is minus 10. So the zeros are something like someone here, something just is like here. If you compare this zeros to the closest or the dominant pole, it's more than a 10 times, right? So definitely this is dominant, and this zero will have no effect at all. Even though that we said that if it sits on the left hand side, on the negative side, we will have an overshoot. But in this case, we will not have an overshoot because it is negligible. Okay, so there's no overshoot. So if I ask you what is the effect of the zero in this case, I will say that its effect is negligible. And we can see that from this figure, like this is like the I know it's not clear, but this is the origin. Here's the origin. This is like MATLAB sometimes draws it like that. So this is 1, 2, 3 poles, and the last one is at 0, really very far away. What do we have? We have a normal response. A normal response, a stable normal response. The 0 has no effect at all. Okay, it has no effect at all. So we have a smooth response, a stable response, not oscillatory, of course, because we have no complex root. So it's a smooth response, as we can see, with no effect. Effect of 0 is what? Is negligible. The same example exactly, but instead of saying 1 over 10s plus 1, what are we using? We are using 10s plus 1. And in this case, 10s is equal to minus 1 and s is equal to minus 0.1. And this minus 0.1, we did not change the poles just for the comparison. And it's asking us to find the effect of the 0 on the dynamic behavior. In this case, you already can see that the 0 is really very close to the origin. So if I just draw my figure here, so the 0 is standing here, and then I have another pole here, and another pole here, and another pole really far away. So the 0 here is dominant, is closest to the imaginary axis. So it will have an effect, and the effect will be overshoot. What do we mean by overshoot? You already can see a comparison here. That means instead of taking a very normal response, what we will have an overshoot. Okay, we will have an overshoot. And actually you can see a very strong overshoot because it's very close to the imaginary axis. It's very close to the imaginary axis. So we can see that it will have really a high effect. Okay, and someone would ask me, well, what if it was sitting here? It will have an overshoot, because it's like not 10 times less than the closest one, but it will have a smaller one. Okay, a smaller one. Okay, so don't worry about it. It will have an overshoot. Okay, what's the difference between the overshoot that I said, the second order process? This overshoot, the second order process, would look more like something that goes up. Okay, something that goes up, and then it goes down, and then it goes up again and down. So that is different. This overshoot is different when we divide A divided by B, right? And there are still more oscillations. Here is just one peak, and then it goes and decays. Okay, and the reason that it does not oscillate because there are no complex roots. So this overshoot here that I have is not because of the oscillation, it's because of the zeros. Okay, so instead of saying slow, so the dominant, the word dominant is still here. Dominant 0, you get an overshoot. Well, let's take an example of where tau A here is less than 0. Okay, if it's less than 0, I would expect an undershoot, or we could call it an inverse response. And in this case, what's the value of S? S is equal to 10. So if you plot my plane, so I'm going to have the poles as like that, and my zeros is going to be still far away. So which one is closer, the zeros or the poles? The poles are very close, and actually this is about 10 times without considering the signs. Okay, we are just looking at which one is closer. So definitely this is closer, and because this is closer, what we will say? We will say that this is dominated by the poles. The effect of the zeros is negligible. So the effect which we thought that will have an undershoot is not, it is negligible. And as we say that, you can see that how far is that 0 comparing to the other 3 poles. And again, a very normal response without any undershoot. However, if I have minus 10s plus 1, in which my s is equal to, my zeros here is equal to minus 0.1, and plus 0.1, and in this case it is really closer to that pole which is the closest, right? And in this case this will be dominant, and since it's sitting on the right hand side of the figure, it will have an undershoot. Okay, and you can see in the figure that we have the zeros here, and these are the 3 poles. So what do we have? We have an undershoot, and you can see this is a very strong undershoot. So instead of taking a very normal process which looks like that, what will happen? It will undershoot, and then it will take a response, a normal exponential response where it decays and it goes to a new steady state value. So what are the effects of the zeros? The effects of the zeros, it's overshoot and undershoot, and it depends on what? It depends if they are dominant or not. So this one is dominant, and because they are dominant zeros, so because you have a dominant zero, what does it cause? It causes an undershoot, or it could be called an inverse response. Okay, great. What else if you have other complex, okay, complex zeros, yani complex zeros that are sitting here? Having complex zeros, we are looking again which one is closer to the imaginary axis, and still these two zeros are closer to imaginary axis, so they will be dominant. However, because they are complex, there will be an oscillation, and on oscillation, that means you will have an oscillation. And you can see there are two things that are participating here. You're having an oscillation. Sorry for that. This is, yes, that's right. So this is an overshoot. I just thought that there's strong, yeah, it's zero here. It is zero. So yes, there's an overshoot, and you can see here poles have negative real roots, so stable. Dominant poles are real, so it has an overdamped behavior, and we already know that is stable, so it is overdamped, right? Definitely. And a pair of slow complex stable does not mean it's underdamped or overdamped. Stable means that it is stable, that it reaches a new steady state. However, is it oscillatory? Because we have no complex roots and real roots, it is not oscillatory because we have no complex root, and that is why it is overdamped. And however, if we have a pair of complex roots or complex poles, I would say, definitely I will have what? I will have an oscillation. And in this case, I had a pair of complex, so it's also an oscillation, but it also has overshoot. So this overshoot is a contribution of oscillation and overshoot. And this is not an undershoot. This is like a continuation of my oscillation process. Okay, it was a continuation of the oscillation process. What else do I have here? If I have system with zero at the origin means what? Okay, zero at the origin means what? It means that it eliminates the effect of the step. That's the only thing that I can say. I cannot say anything. It doesn't have a meaning that we really can rely on. What do we mean? Just to clear it. Zero at the origin, that means my numerator is s, and then for example I have s plus 1 to s plus 2, right? So if I have a step input, this s will eliminate the effect of the step. And that's what it means, and actually there's not a lot to talk about here. It eliminates the step function. Okay, so this is what I have for poles and zeros. This is what I have on poles and zeros. So what I'm going to get to you in the exam, I'm going to ask you if we will have an overshoot or undershoot, or we will have a stable process and unstable process. And by that, if I have reached to this stage here, I would like to have the opportunity. I think so. I will do that in a different video just to get more prepared for it. Well, I'll try to explain where we are standing now. Okay, we have taken the effects of poles and zeros, and after taking the effects of poles and zeros, and I think so it's a good time that we can get to the approximation of higher order systems. But before I get to that, I need just to make sure that you know where we are standing and why we are taking approximation of higher order system to lower order systems. Right? There's a reason behind it, why we are doing it. Why did the scholars work hard to approximate higher order systems to lower order system, or not mainly to first order or second order systems? There is a reason behind that. Okay, there is a reason behind that, and until then, we get to that stage, this is what we have for poles and zeros. We have solved some examples for poles and zeros. Okay, so what is left for today? Okay, what is left for today? So let's see that. I think so that I need to open the PowerPoint that I have. So just going to the system here. Okay, so the supporting teaching materials, chapter number 6. Yeah, that's the one I was trying to open. Okay, so looking at chapter number 6, I just want to show you the effects of poles and zeros. So that's it, where I have the cases that I already mentioned for poles and zeros. Sorry. So here's a very nice figure. Just shows us the effect if I have the effect of all things together. Okay, the zeros and the poles and so on. So I have tau 1 is equal to 4 and tau 2 is equal to 1. Okay, so in this case, if I have tau 1 is equal to 4, tau 2 is equal to 1, which means I will just write that because it's not clear. 4s plus 1 is equal to 0, so s is equal to minus 0.25, and then I have s plus 1 is equal to 0, and this means that s is equal to minus 1. So I have two negative poles, no complex roots, so definitely it will be a stable process. Okay, it will be a stable process, so there will be no oscillations, no oscillation. So we are just talking about the process as smooth, okay, stable, and it is smooth. Why is it stable? Because negative real roots. Why it is smooth? Because there are no complex roots. Okay, and based on that, now we are looking at the figure here. What is the value of tau A? I have different values of tau A. So if tau A is greater than 0, I will have an overshoot, right? So what do we have here? So let me start with 16. Very big tau A. It will have a big overshoot. And why it will have a bigger overshoot? Because, for example, for tau A s plus 1, 16s plus 1 is equal to 0. 16s plus 1 is equal to 0. You will have s is equal to minus 1 over 16. And minus 1 over 16 is really very close to the imaginary axis. And this is why it has a big overshoot, and it will have in comparison to the other two the other two poles, which is minus 0.25 and 1. Okay, so this will be like minus 0.25 and minus 1, and this is minus 1 over 16. Imagine, right? It's not 1 over 4, it's minus 1 over 16. So definitely it will have a strong effect. And then going to the second case, which is minus 1 over 8. Okay, again, it's like still closer than the minus 1 over 4. So it will have a big overshoot, but still less than the one which is closer. And then when you go to 4, actually 4, which means that it exactly sits on this pole. So this 4 means that I have something like that. So I have a pole and a 0 sitting at the same place, right? So both of them like are dominant. So talking about that, we will have something like looking like a critically damped, right? Like no overshoot, no undershoot. It's like straightforward, but it looks like there is an effect that's pushing it a little bit up there. Of course, with the 2 is still greater than 0, and again I'm talking about a pole. I'm talking about a pole this time. I'm talking about a 0 that's sitting between two poles, and I told you that it will have an effect as long as it's not a 10, about a 10 effect. So it will still have an effect, and you can see the effect. It is like still have an effect than the other ones, right? Which are sitting here. It's still a little up there. And if you go to my 1, which is minus 1, which is sitting with whom? Was sitting with the other pole. This time it's sitting with the other pole here. So it will really have like no effect. If it's 0.5 going further away, it will have no effect at all. However, if we have a negative sign, of tau A, we will have an undershoot. And -4, we will have a stronger undershoot. And the stronger undershoot actually with -4, even that it was sitting somehow. If you look at this thing again, this is like of a same distance, and both of them are dominant, so we will have some kind of an effect, which was different, by the way, when it was on the other side. There are always reasons of why this is happening. You cannot take my word as definite, telling that if they are at same positions it will have no effect or it will have similar effect. It's not like that. But this just gives us an indication. It gives us an indication if you're going to have an undershoot, overshoot. And in this case, the indication that's closest to our mind that we will have an undershoot because it is still dominant. Okay? So that's what we stated, and we already explained the effects of poles and zero locations. And the poles, again, just a summary, it is donated by this X here. It could be on the right hand side or the left hand side. If it is on the right hand plane, if you can remember, it will be not stable, and if it's in the left hand plane, it will be stable because I have negative real parts. And about the zeros, it depends on the zeros. If it is closer or dominant to the imaginary axis, it will have an overshoot or undershoot. This is the case that we have discussed, and we showed how we are going to derive this equation here, and so on. Okay, so that is the effect of poles and zeros. These are the effects of poles and zeros. Tomorrow we are going to start with a time delay and how. What do we mean by time delay? Actually, we took what do we mean by time delay, but we are going to take the approximation of time delay. So the idea of approximation is just starting in our head here, and we are going to take this next time. So till then, thank you very much. That was our topic today, effects of poles and zeros. I hope that you have gained a lot of what you have taken today. Thank you very much. Thank you.